In this video, we're going to investigate the solubility of copper 2 hydroxide in an ammonia solution. And to start, we have part A, which is asking us about copper 2 hydroxide and a potential complex ion. And we have K values for each. And as we're getting started, even if this question doesn't prompt us for this, we should always put down our chemical reaction and our equilibrium expression for these relevant constants. Remember that if it's a KSP of something or if it's a KF of something, these correspond to very specific reactions, which will get us the form of our equilibrium expression, which is what we'll use to solve, any kind of setup that we would have further. And so starting with the solubility of copper 2 hydroxide, this is what we're looking for, the solubility, and here is the KSP value for that. Now, we also want to get the formation of this copper tetraammonium complex ion for which we have a KF. And starting with the solubility of copper 2 hydroxide, we want our reaction and the equilibrium expression. This is the reaction, and it's simply copper 2 hydroxide that's dissociating into one copper 2 ion and two hydroxide ions. And with this, we get our equilibrium expression. It's just products over reactants, and this should be a similar looking form to what we are used to dealing with already when it comes to solubility. Formation of complex ions is a bit of a newer topic this week. We dealt with solubility last week. This is sort of a newer equilibrium, but nevertheless, getting the reaction from the species that's being, in this case, formed is the first step. And as it is a formation, we know that this is a copper 2 ion. It's 4 ammonias. We know this from the structure of the complex ion itself, and that these form the following. The equilibrium expression is just products over reactants again, and here it's a KF. Note that the complex ion is formed, not dissociating or degrading. It's a product, and the KF is just products over reactants. Don't forget to get your coefficients as exponents in your equilibrium expression, and I just want to draw attention to the idea that when we have this product over reactant form, this is how we are setting up our K. Okay, so now the question is asking, when we put copper 2 hydroxide into ammonia, we have a formation of the complex ion. And we want to state the chemical reaction and equilibrium expression for this and the value of its constant. And a technique we use for this, and one you should be familiar with by now, is that we have our KSP, our solubility of our copper hydroxide, and we're going to add to it the reaction that's the formation of the complex ion. And we have both their K values. If we do this, we see that we get a net reaction, which here is the copper 2 hydroxide in ammonia, which is going to form hydroxide and the complex ion. And so it really does show ammonia degrading the solid copper hydroxide to form the complex ion and then these hydroxides that are liberated. For this, we know that the K net is equal to the KSP times the KF. This is something that we really want to be familiar with. If we add chemical reactions, we multiply their K values. And once we have that, we can get the value of the equilibrium constant. This is simply through the KSP and the KF. The equilibrium expression will reflect this net reaction. Let's call it K net, and that will be just products over reactants, again, making sure that we catch those coefficients as exponents on the equilibrium expression. All right, now we want to do a calculation. Let's calculate the molar solubility of the copper 2 hydroxide in ammonia. And let's bring together all of that we calculated previously. So here's our reaction, here's the equilibrium expression, and here's the actual value of our K net. And again, once we're here, we're just setting up a nice table like we've done many times before. We want to be mindful of the stoichiometry and what happens as we have a change to equilibrium, but we have our K expression and we have our K value, so we'll be able to solve. Now, for our ice table, remember this is all in molarity, but I'm going to omit that capital M in the table just for clarity. Initially, let's say, start with the solubility of copper 2 hydroxide. We'll call that S. The ammonia is 2 molar, and we have none of the other two products to begin with. The change, by definition of the setup here, is that we'll say, well, S dissociates. That's the definition of the molar solubility. What's the amount that's going to dissociate to get us to equilibrium? Therefore, if S copper 2 hydroxide dissociates, 4S of the ammonia will be consumed, S of the complex and 2S of the hydroxide will form. Equilibrium is just I plus C. The C row is the challenging part, and we're left with the following. Now, note that this reaction is highly reactant favored. It's got an exponent of 10 to the negative 7, and therefore we should expect this shift is going to be small, as most will still remain on the reactant side. And because of this, let's try our 5% rule, right? And basically what this is saying is that the change from 2 molar ammonia is likely to be insignificant compared to the 2 molar itself. And so here's the approximation that we'll use. This is something that we've done before. Let's just call the equilibrium concentration of ammonia 2 molar, and we'll have to check this at the end. This really significantly improves our calculation. We'll do the following, and we solve for this as S equals 1.23 times 10 to the negative 2. This one is pretty straightforward. We only have S in one place, so the algebra, make sure that you're able to get that value too. But what about that 5% rule, right? Is 2 molar really pretty much equal to 2 minus 4S, right? Is 2 about equal to 2 minus 4S? And for this, let's check it, right? Let's say 4S divided by 2. This is essentially saying what fraction of 2 is 4S. And if this is less than 5%, we're going to be okay. We plug in our S, and we end up getting 0.0246, which is 2.46%. And this is okay, right? This is to say that 4S is only 2.5-ish% of the 2 molar that we had originally, and that's less than 5%, and this approximation is acceptable. If you want to go about solving this as the more complicated form, you can do that as well. Your answer won't be very different. Finally, we want to describe, well, if the molar solubility in pure water is the following, how does this compare to the solubility in 2 molar ammonia? And we want to describe why. And so let's just take the solubility values in ammonia versus in pure water. In pure water, it's on the order of 10 to the negative 7, and in ammonia, it's on the order of 10 to the negative 2. And so how do these compare, right? Well, in ammonia, it's actually about 100,000 times more soluble, a change of 10 to the 5th. That shows that in ammonia, it's much more soluble than in water. And if we think about this, it should make sense that this is the case. If we add ammonia, it's going to draw copper-2 away from the copper hydroxide, which is going to allow for more complete reaction. We can even just look at this net reaction where if we add more ammonia, that's going to cause excess reactant and a shift to the right, which also will decrease the amount of solid copper hydroxide on the left.